session. Good afternoon, folks. It's about 4:20 right now, and we're going to get started pretty close to 4:30 again. If you have any questions before we start, though, do feel free to put them into the chat. Thanks. Good afternoon, everyone. We're at 4:25 p.m. right now, and we're going to be starting pretty much at 4:30, so another 5 minutes before we start. In the meantime, there is going to be a welcome clicker question if you'd like to do that while you're waiting. Also, if you have any questions before we start, feel free to put them in the chat. All righty, we are at 4:29, so we'll give another minute for folks to arrive before we start the actual lecture part. For those who are in the Toronto and Kingston area east, I hope you've been doing all right, given all the snow and crazy weather we're having. I'm not looking forward to the flash freeze they're predicting for tonight. My microphone does seem to be on. I have forgotten in the past, but I see it on now. Let me just double check. Okay, confirmations. Yeah, it's the input I wanted, so So yeah, check your audio levels. Thanks. Alrighty, so we're at 4:30. So again, because we're at the end of the afternoon, I don't want to hold you longer. Just do a quick spin back to that survey. Back in person. Interesting. It's actually a lower number for in person than there was last week. But I wasn't sure how that would pan out. All right, those only the early arrivals. So on the positive side, schools have gone back, things like that. So, and some of the vibe I was getting, we had a department meeting for the mechanical engineering department yesterday. And certainly the vibe there was, without any firm dates being given, if anything, people were looking at coming back earlier for some small things in person. So it's looking promising. Again, there's another few weeks before they have to make their call, but it's looking promising so far. So that is the only news that I have to share. All right, let's get into the, excellent, I'm glad you found out the audio thing. Let's get into the lecture material here. All right, one last setup thing here. So what we're looking at this week are vector spaces, and the idea behind a vector space is it's the things that we've already worked with. So the real numbers, the set of vectors in 2 dimensions, vectors in 3 dimensions with real numbers in them. And the idea that we can add those together and still get, you know, if I add 2 vectors together, I get another vector back. If I add 2 real numbers, I get another real number back. And also we can multiply any of those things by a real number as well. Whether they're real numbers themselves or vectors. And we also hinted at the other applications like functions. We can add functions and get functions back. We can take scalar multiples or real numbers times functions and get new functions back from that. So we've seen and worked with frameworks like that before. And what we ended up, when people started looking at the patterns in those kinds of systems, they said, well, what makes this kind of unique? Given that if you actually think about the plus that we're doing or the scalar multiplication, it's a little different for all of those cases, whether it's functions or 2 or 3D vectors or a single real number. We're doing kind of the same thing, but it's not exactly the same thing. So what are the rules that let us instantly recognize that, yeah, plus means what we think it means, and it applies to this new environment as well? And what they tried to do was distill out the key properties that make plus behave like we expect plus to behave, and came up with this set of axioms for vector spaces. So associative and commutative we talked about before. Again, those are not major features in what we're going to do with it, but they're just important characteristics, and we use it all the time when we're actually doing mathematical manipulations. For our purposes today, one of the key elements is going to be that when we take 2 elements of our set and we add them, we get another element of the set back. So we can add any 2 elements we like and still get an element back. That's what we mean by it being a well-defined function. The same thing for the multiplication by a real, by a scalar multiplier. The big one that tends to affect us is having the 0 vector or a 0 element in the set, where if I start with 1 element and I add this 0 thing to it, I get the same thing back. We're going to see that show up in an interesting way in an application later on today. And the other idea being the negative of one of the elements. So if I take any element, there should be some kind of opposite of it, negative version of it. And when I add them together, they give me the 0 element. Those are the big ones. And also multiplying by the scalar 1 should also, or by the real number 1, should give us the same number back. All right. So we left off last class after looking at a number of examples, and I did want to touch on this big one here, this idea of the set of continuous functions that are infinitely differentiable. So that's our C infinity set. Sorry, I'm just trying to reset myself so I can write more clearly here. Set of continuous functions. And if we have to, we don't usually do this. Again, context is usually the key for this. These are functions that are defined on the real numbers. So this is not like 172 right now, where we have functions of 2 variables. This is continuous functions like sine of x, e to the x, things like that. And also that infinity there means that they are infinitely differentiable. So again, this includes things like sine of x, this includes e to the x, it includes the polynomials. So it's a pretty broad set of functions that we can work with. Now we have to be careful when we start doing this, and this speaks to that idea of plus means slightly different things when we apply it in different contexts like this or on different sets. So we have the set of continuous functions, and we're going to define addition as the point by point. Did I do this yesterday? I feel like for some reason I'm having a flashback. Anyway, point by point addition. And so what we mean by plus is it's a function that takes in something from C infinity, sorry, two things from C infinity. So this is our set notation where these are our inputs and it gives us back another function. And the idea is if we take two functions and we add them, what we get is the function itself evaluated x plus g of x. So eval both functions at a point, and then add the real numbers, real values of each function. And again, this is getting into details that we don't usually think about, but if you think about how you calculate, I'm going to do a graph, let's do it this way. If I said h of x is equal to sine of x plus x squared, and said evaluate that or graph it or do anything with this really, what you would do is you'd say, well, if I'm graphing it, I'm going to evaluate this function at a bunch of points. Well, I'm going to evaluate the sine function at some points and then the x squared at the same points. I'm going to add those answers and add those values together, and that's going to get my graph generated. So again, this is all what we normally do, but it helps to make it explicit when it's, it's slightly different than what we might do with a vector addition. And basically the same structure applies here, same point by point. Scalar multiplier, scalar multiplication. Again, if we think of the example of f of x being sine x versus some other function being like 3 sine x, what does that 3 do for us? Well, it takes, for any x value, I find the regular sine of x and then I multiply it by 3. I scale it up by 3. So it's for every single x value that we have on the real line as the inputs, we do this calculation. So we can define that nicely. Then we get into the other ingredients that we talked about, like the zero element. And what we have here, or what, just a reminder of the requirement, we need f plus the zero element to equal f. And then the subtext for this is because it's point by point, it's for all x's. For all x's. So imagine plugging in this. I think most of you have a good idea of what this would be. The zero element in C infinity is the always zero function. Let's call it hg. Yeah, let's call it h naught of x, which is equal to 0 for all x's. So it's literally the flat line at 0. Keep that on there. H naught of x, h0 of x, really. So this is always zero function is something that we can add to any other function, any other graph, and we get the same graph back. We get the same f of x back. But again, it's one of these things that kind of shows up sometimes in calculus, the difference between 0, the number, versus 0, the function for all x's. Those are slightly different things. You have to be careful, and we try to be careful about that anyway, more careful in linear algebra than we often are in calculus. So again, when we think of this 0 thing here, we'd often in linear algebra put a little vector on here or write it as this extra, this new label I just put on there, h0. to say it's not the number 0 that we're adding here. It's actually the 0 function, the always 0 function. Negatives, fortunately, work about just the way you expect. So if we need f plus the negative of f to equal the 0 function, again, or that, call it h0, then our negative function, negative f, can be built by computing -1 dotted with f. So it's a scalar multiplier by -1. Not a huge shock here. If you want to flip the graph of sine of x across the axis, across the x-axis, if you want to flip it, you just multiply everything by -1. That exchanges the positive and negative y's, and away you go. This is actually going to be a little theme, I think, for next class, where we say this negative and this negative end up being the same. That's why we use our notation, but it's actually, it can be a little more subtle than that sometimes. But here it's, yeah, if I have one function and I want to build another function that cancels it, that adds it up to 0, then we just can take the function we started with and multiply it, scalar multiply by -1. All right. Okay, so let's just gather ourselves up here and look at the vector spaces we've seen. So we saw that the reals and the reals, with 2 dimensions, 3 dimensions, or really n dimensions are all vector spaces. And again, those will add a little usual thing about the plus and scalar multiplier operators. Reals that C infinity functions. And we didn't cover it, but P1, P2, Pn polynomials have degree n, which are part of the C infinity, but a smaller set. Those also are vector spaces. I can take quadratics and I can scale them by real values. I can add quadratics and get quadratics back. There's a 0 function in there. It's the same 0 function there as it was for C infinity. So there's a variety of stuff in there. And to contrast, what do we see that didn't work? Well, if we had the natural numbers, they didn't work. Integers didn't work either. And what else do we see? We saw, the set, let's put the set in here. The set of all x's that are reals, if we limit ourselves to x greater than or equal to 0. And why was that? This was missing the negatives, negative x for all x. Missing negative x in some cases for some values. So that was a problem. And this was, integers had a problem with not being closed, or the dot scalar multiple by reals led to a times some number not being an integer anymore. So if we picked a nice integer like 2, but we multiplied it by something like 2.5, well, sorry, that's a bad example, 2.4, then when we took that product, we got an element that was not in Z, pardon me. Let me highlight that, not in Z. And actually, the same thing is true for the natural numbers. It had other problems. It didn't have negatives. It didn't have the scalar multiple working, whole pile of problems. So if I have the intuition now, so I think another page later on. So those are some building blocks, and sort of think about how those are different. These ones here are sort of granular in the sense that they have distinct points that are separate. And that's very different from the reals, which had that continuous real line representations, and same thing for 2D and 3D. Those are continuous kinds of spaces. So somehow we need to have continuity or we're out of luck. And we also seem to need the whole range of values. We can't just limit ourselves to pluses or minuses here. Let's take a look at the next example, though, which gets into some other way to limit things and to see if it matches or does not match what we're expecting here in terms of, is this a vector space? So what we're going to look at is a vector space that's a subset of R2, so the XY plane. And what we're going to look at are all the elements in the plane such that, again, that's our little colon that says, I'm not going to take all of them. I'm going to take these elements so long as they satisfy the restriction that x plus y equals 0. So I have a quick clicker question on that. This is really taking you back to the calculus side of things. What is that set? What does it look like if you try to draw it out? Flip over my phone here. Let's track it that way. There it is. Better work pretty hard. All right, that's not working on my phone, so we'll go back to the computer here. Lovely. Okay, not too bad. Interesting. Okay, so we're seeing the straight line through the origin, bottom left to upper right as the candidate. Let's pause that there for a second. And what we're going to do is just break this down a little bit, because we want to have the set of all points satisfying x plus y equals 0. Again, this is sort of a flashback to calculus where I don't know how to graph that. That's not something I'd look at and know how to graph. I do know how to graph it if I make it y equals. So if I isolate y, then we have all our intuition and experience that helps us now. But if we do that, of course, we have to take the x over the other side, and guess what? It turns negative. And so right away we go, oh, that's the graph of y equals negative x. That's a straight line down like that through the origin. Let me nudge the origin up. There we go. So this is the line y equals negative x. And this set of points on the line is what we're calling V naught here, V0. We'll see why I want the 0 there in a second. But yeah, that's what it is. So it's actually from the upper left, sorry. I think I had the same line twice, didn't I? I just realized I didn't mix and match the answers. Anyway, so this is a straight line. You're totally on the mark, and I apologize for not thinking through that question well enough. So upper left down to bottom right. That was the graph I was aiming for. So none of the answers are right. No, I think I had the same thing reversed, right? Yeah, straight line from upper right to bottom left and bottom left to upper right. It's the same thing twice. All right. Oh, choice last minute thinking. All right. So is this a vector space? I mean, R2 is. We know if I'm allowed to use all of these elements in XY plane, I can add them, I can scalar multiply them, that's all good. How about these ones? In principle, we would need to show that all the axioms for this vector space are fulfilled. We have to go through that list of 0, showing that these things are well-defined functions, and all the plus and minus. We'll show a couple of these. In fact, this is the one that often catches us right at the gate, so we might as well take a look at it first, in which case, yeah, clicker went down for me on my phone. I don't know what was up with that. So fortunately, that was our last question for the day.
You're still sharing the clicker screen. Just so
Oh, thank you. There we go. Much appreciated. Where was I going with this? Right. So right back to this, we have our set. Is it a set that satisfies all the axioms for our usual vector sum and scalar multiple for vectors? So the one that usually trips us up out of the gate is, are these well-defined functions? And what we mean by that is, if we add two elements of V0, do we get another element of V0? Of V0. And likewise for the scalar multiplication. And fortunately, the answer is, in fact, here, yes. And we can prove that. So so usually we'd say let pick two elements of our set. And usually we'd use like V and W. Don't put those down yet, quite yet though. What we're going to do is actually make this concrete because we know we're working with pairs of variables, X and Y. So let's call it A and B and C and D. Be two elements of this set. So I have two elements of the set. Then from the usual vector sum, AB plus CD is equal to, well, our usual vector sum says add component by component. So A plus C and B plus D. There we go. But we know, and a question now is that element in this set still? So is A plus C, B plus D in V naught? Well, the question that's equal to that is the X component of it and the Y component of it. This is the Y component, this is the X component. If I add them together, do I get 0? Because what every element in this set shares as a common feature is that if I take the X component, the first component, and the Y, the second, that I get a 0 sum. Is A plus C plus B plus D equal to 0? Well, the answer is yes, because we know that A plus B equals 0. Because AB, we're running out of space here, is in V naught. Oh, that's so tiny. We said that we're going to start off with an element in this set to start with. And so our AB was one element. The element has then the sum of its two components are 0. And we also know, of course, that, oops, that was weird. We also know that C plus D equals 0 because CD is in V naught. So if I package that differently, A plus B plus C plus D is equal to 0 as well, right? So I just take A plus B, that's 0. C plus D, if I add that, that's another 0. I can still get 0. And then we go to over here. So I'm just going to rearrange this. This is where the associative comes in handy. I can associate these differently and package it like this. Even put brackets around that. And then, so the vector A plus C, B plus D is also an element of V0. That was a long way. So the question we're trying to answer is this new thing that we built in this new set. And then we basically start with the stuff that we know. So really, if I was doing a proof, and we'll do some more of these tomorrow as well, this is sort of give us a goal. This would be the actual proof. If we know that this element's in our set, then we can make some statement about it. So some relationship between A and B and 0 here. And the same thing for the other one. Oh, okay. I know where I'm heading. I want to get to some equation like this, but how do I get there? Well, I can add them step by step and say, okay, if I add them, I still get 0. If I rearrange them, I still get 0. Oh, that means if I put it as these two components, I could build a vector like that and it'll still be in the set. And that's exactly what we got from our regular vector addition. So it's that kind of proof that you'll see in some of the tutorial problems this week. We won't go through all these specifically. Associative and commutative just tend to be boring when we're using this regular operations. It just looks like you're doing regular math, you're resetting things. Again, the one that often is a trigger for us in our sets is the 0 vector, whether we have one or not. What we can imagine is trying the 0, 0 vector as I'm here going to put the line over it for the handwritten version. And we're going to let A, B be an element of V naught. Then AB plus 0, 0. And what we're using here is plus 4 vectors. So we would get A plus 0, B plus 0. Inside each of these things, what we're doing is adding with reals because we're just down to a regular number. Reals. And of course, if we add 0 to real numbers, nothing happens. And so we get back to the original value. So that's equals original value. So 0, 0 is the 0 element or the 0 vector for this set. Not a big deal there. And again, most of this kind of fits. I want to take a look at a contrasting example where the stuff breaks down a little bit more. Yes, these are other features laid out. So in the end of the day, what we end up finding is that V0 is a vector space. In terms of expectations in the course, we do not expect students to do all of these. What we would do is give you a prompt and say, again, probably not these ones. These are our two favorite ones, that if find the 0 vector and show that it satisfies the properties of a vector space. So you'd have to find the 0 vector and do this kind of proof. So grab an arbitrary element. So it can't be a specific one because 0 has to work for any vector you like. So pick an arbitrary element, go through the calculations involved in adding 2 vectors and show that you start and end with the same value after adding 0. Where does that break down? Well, if we just make one little tweak to this set, everything falls apart quite nicely. So let's take a look at this value or this set here. We have all the points in a 2-dimensional plane, so XY plane again. And the only difference is now that X plus Y doesn't add up to 0, but it adds up to 1. And so if we take a look at this set, that's equivalent to the equation Y equals 1 minus X, which is almost what we had before, only now it is offset a little bit. So this is the line Y equals 1 minus X. And all these points, all the points on the line are in V1 here. So that 1 is just indicating, hey, it's the one that has X plus Y equal to 1 instead of 0 like last time. And I'm hoping some of you have the, are already feeling some of the issues like, oh, we needed a 0 vector. It's not in this set anymore, so that's going to be a problem. We actually have even more problems than that. So let's start with the fundamental one. Do the plus and dot operators work in the way we need them to? And again, let's use the, actually let's do the scalar multiplier this time just for variety, because I think it's going to break down to, yeah. No, neither of these actually work for this new set. Why not? So let's let AB be an element of V1 this time. So we're going to start with our set and we're going to take one element of the set. And because it's in this set, that means that A plus B equals 1. Okay. Here we're trying to show a counterexample. So we can pick a specific value if we want. Let me make that explicit. We want to show that the scalar multiplier dot is not a function here. So we look for a specific, any single counterexample. Oops. In proofs, showing things are true for everything, you have to keep everything general. If you just want to show there's one break in the dike, one hole in the dike, then all you have to do is find one example where things break down. That's straightforward here. For example, if we let 2.5, let's let K, let's call it K, be 2.5. Let's do that. Let's make it a nice round number, like 5, which is an element of the reals. Then K multiplying AB must be be in V1 if V1 is a vector space. We can't just, what makes a vector space is that I can freely multiply by any number I like, any real number I like, and get another element of the set. I can do that. I can multiply real numbers by real numbers and get real numbers back. I can multiply vectors by real numbers, I get the same vectors back. The question is that true here? No, is the short answer, but let's find out why. So if we go and do the calculations, but 5 times AB, so actually putting the number in here, is 5A and 5B. And that's just using the regular scalar multiplication on vectors. So if we do that, we get 5A and 5B, but 5A plus 5B is equal to, why am I looking at this? Because what makes an element of this set is the fact the sum of the two coordinates equals 1. However, I know that this A plus B here equals 1. Do this in red, sorry, green, equals 1 because AB was in the set. But now I'm multiplying by 5. And that is a problem because that's not equal to 1. So when I look at this new vector, 5AB, and I try to apply this test, hey, when I add the coordinates, do I get 1? Well, no, when I add the coordinates for that set, now I'm getting 5. And so trying to think of generic here. Let's call it this way. 5AB is not in V1. And that's a problem because we don't have a vector space anymore. We have to be able to add things safely. We have to be able to scalar multiply safely. And we just blew that up here. So right away, we can say that V1 is not a vector space. V0 was, all it took was this little transition here from having x plus y equals 0 to having it equal 1, or in fact, anything that's not 0, it would cause all the same problems. So somehow that 0 is a magic thing. And the fact that it shows up in the definition, the axioms of the vector space is not a shocker. And you'd actually find out that if you wanted to look deeper, so this is not necessary to look for more faults, because any missing axiom, any single mixing axiom, any single mixing axiom is enough to disqualify a set. So we don't have to look for this, but you can pretty much guarantee that you would run into more problems with this because the 0 vector is not in V1 either. So the 0 vector would be missing. You can't really even define a negative without the 0 vector. It might have the other properties, but it certainly doesn't have that one. So there's a whole bunch of things, or at least there's more than one thing that's going to go wrong with this V1 set. So as soon as we find one, though, we're done. All right. You mean this one here? Just confirm here. Oh, that's that page. That's that page. Oh, you'd have to prove there's no 0 vector. Here it's just more by context. We really relied on that 0 vector in the last set, and now this one doesn't go through there. So it seems likely that the 0 vector is not in there. But yes, we'd have to prove that if we were asked. How do you? Excellent question. So how do you know when to prove it wrong or prove it right? So sometimes the question will say, show that this is a vector space by showing all the axioms, or support your argument that this is a vector space by showing these 2 axioms. Or it'll say, show that this is not a vector space and pick one of the axioms that you can illustrate. That's basically what we did here. So we would ask a question like this: does it satisfy this criterion? And that's why we're trying to build a little bit of intuition right now of, you should have an idea before you start of which road you're going to be going down. Is this a yes, 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 it's a vector space, or no, this feels dodgy. Sometimes you might get surprised, but more rarely than you might think. So the idea is you should have a direction, and then you start down the direction and you try to see if things fall apart. If you're trying to do a proof like the last one where things did work. So you try to build these calculations and say, can I make it from the start to the end that I'm supposed to get to? And if you feel like some piece is missing, then you're like, oh, maybe it's not a vector space. Then you go looking for a counterexample. So it's usually, yeah, usually you should have some intuition when you start which way to go. Try if you think something is a vector space or does satisfy some theorem or some criteria, you start going down that road in the general case. And then if you start feeling like this doesn't look like it's going to work all the time, that's when you fall back, change your mind, and maybe find a counterexample. That's usually the strategies. Yeah, I don't know what's going on with my lighting system here. Whew. Let's try that. Here, I'm just red now. And sorry, so on an exam, no, if we try to be legit about this, if something is not a vector space or some rule is not being satisfied, some set is not a subset of the other thing, as soon as you've proven it through one statement, you're done, because that's it. You've shown one counterexample, then you know the answer and there's nothing more to be said about it. So typically it's a lot of work to show things are true because you have to go through a whole list. Where showing something's not true, it's like, oh, this one thing here doesn't work, so you're done. So it's actually kind of a nice shortcut if you know that you're looking to prove something's not true, if you can find a counterexample. All right, I do have some other things I desperately need to get through today. Otherwise, we will not. One of the notes won't leave you in a good position to tackle the tutorial problems and so on, and web work. All right, so what seems to help make a vector space different from non-vector spaces? I'm actually going to leave this a little bit up to you because I've got my own sort of headspace, but I'm not sure it translates well to communication. I would say look back at those lists here, and now that we can add a few more things here, this V0 set down the line here is a vector space. It'd be better if I actually drew that with colored lines there. There we go. Whereas V1 was not. So just that compare and contrast. Try to find features that work for you. What does it feel different to be in this column versus that column? And then we're going to stretch things one step further. Yes, we're going to stretch things one step further here. And just for your own reference, we're going to call this, we're going to refer to this a few times. We're calling it W for the weird vector space. It's actually not weird, but it's good. It can blow some people's minds at the beginning. So let's start off with, what is it? So W2 is also a subset of the XY plane, but we're only going to allow the positive X's and positive Y's. And that should already be raising some red flags here, right? So it's all the numbers here where X is positive and Y is positive and not the axes, right? That's W2. So if we use the usual addition and scalar multiplication rules, is this going to be a vector space? I missed a whole bunch of things here. All right. Is that a real vector space? And the answer is no. And one answer is because the zero vector is not in W2. So if I take some element AB, and I want to add something to it, add the zero vector and get AB back, I need this to be 0, 0, but 0, 0 is not in our weird set. All right. So, oh, we're done, right? That was easy. This is not a vector subspace. And again, you can kind of feel that intuition. It doesn't have the zero vector in it. It doesn't have sort of the plus and minus. However, we're going to go into sort of exponential world here for a second. We're going to make up new rules for addition and scalar multiplication. Here's how that's going to work. We're going to blow your minds by redefining what plus means. And again, for those who go into heavy duty programming languages. This is like redefining operators. It's totally valid. We can do this if we want. And as long as we're careful about it, we can see this actually does give us a way to use that same space. So again, we're only going to use points in this part here. That's our W2. And the 2 just goes to the fact that it's part of R2. But we're going to define plus a little different. And we're actually going to define plus as our plus here is element by element products. And yes, this is new math. Not the wimpy stuff that politicians complain about. This is the real new math. So if I add in this new world 2 numbers here, what I'm going to actually compute is not what we usually think of as sum, but we're going to do this new thing. We're going to say, when you say plus, I'm going to multiply the first components of each vector and then the second components of each vector. And so what does that look like? Well, and sorry, often in web work, you'll actually see this defined as some new symbol, like a plus with a square around or something, just to remind you, this is not the plus you're expecting and making you think about it twice. But it's straightforward to do if you want to do it. So we just have to take this number here, 1 and times 3. So 1 times 3, comma, 2 times 4, and that's 3, 8. Sure. Okay, we can do it. We can do that for all these things. This would be like 2 times 4 is 8, and 2 times 5 is 10. 4 times 2 rather is 8. 5 times 2 is 10. Like, oh, hey, hold on. This is commutative. These are the same values, just swapped in order. So that's a nice little example of commutativity, which is good. And if we do this, haha, yes, someone's on that, perfect. Right, the red flag, you shouldn't be doing this multiplication here at all, this addition at all. Off limits. Why? Think about it for a sec. Look at this, look at your set, look at this, look at your set. Oh, right, 0, 5 is on the axis. It's a point up here. 0, 5 is not in our set. 0, 5 is not in W2, so we don't really care about it. We're not going to do multiplication with it. We're not going to do addition with it because it's not in our set. And if you think about that for a sec, if I take any 2 positive numbers, because that's what W2 is, any 2 positive real numbers, and I multiply them together to get the X component and the Y component, I'm going to get another positive number. So actually, that seems okay. As long as I never let a 0 in, that's okay. I'm never going to let zeros in because I'm only taking positive values. Then I can do this strange version of plus. Let's take a look at the next one. Scalar multiplication. How does that fit in? Well, this time, if we take a number times the vector, we're going to put that real number in the exponent instead of as a multiplier. Sure, fine, whatever. So let's try that out. So that would mean here 1 squared and 2 squared. We would take this leading 2 and we would apply it to each of these components separately as an exponent this time, and we get 1, 4. Sorry, taking a step back. This is addition. This is what we're, I was trying to reinforce it every time we went through the earlier examples of saying, this is a 2-dimensional vector using the usual addition and scalar multiplications. Now we're saying, whoa, we can change that. I will be very clear and remind you that what we mean by plus now is not the regular plus that you've grown up with. It's a totally fine version of plus in this new world we're living in, but you just have to be careful with it. It's not the plus that you're expecting, but it is a plus. We're going to have an addition operator. I can add to any 2 elements of this set that I want and get another element of the set. Just put air quotes around the add every time you say it in your head. That's all we'd ask. And just like here, I'm going to multiply in air quotes by real numbers. The way we're going to do that is we are going to put that as an exponent in here. So 0.5 cubed and 4 cubed, and that's something nasty. 125, I think, and 64. Oh, little warning maybe. What if we have a 0? Is 0 bad? Actually, no, 0 is fine because we should be able to take any real number and then any element of W2, sorry. So yeah, we couldn't have zeros in the XY pairs, but we absolutely have to allow zeros in this multiplier. So is that okay though? Well, 2 to the 0, oh, actually that's fine, yeah. 2 to the 0 is just 1. Anything to the 0 is just 1, as long as it's a positive thing to start with. And so that's the way we go. Let me catch up here. There's a lot of chatting going by and I'm missing some of it. So why didn't the addition work in the other one? Addition actually was fine. If I took any two numbers in here, any two values, and I added them, I'd get another value in the set. This would break down because there's no 0 and because there's no negatives on regular addition. If I said, let's take the vector 2, 1, 2, 1, and what's its opposite? Well, I'd want to use -2, -1, but that's not in the set. So addition is fine in W2, just not zeros, the scalar multipliers, the zero vector inverses and scalar multipliers. Those are the things that fail. What are the conditions to change it? You just make them up. No, that's really what it is. So if someone comes along and says, here's a set, here's what I mean by plus on that set, and here's what I mean by scalar multiplication on that set, that either is a combination that makes a vector space or it's not. Either it is or it isn't. And what we're teaching now, going through now, is testing, showing how we can test whether that is a vector space or not. So anytime someone wants to come up with a new version, and you'll see this in your web work of what plus means on a set and what scalar multiplication means, the question then is that a vector space, yes or no? And knowing how to do that analysis. So, alrighty. So yeah, these guys are fine too. Like we can do fractional powers. So 2 to the -3.1415, and that's a number. It's a nice real number. So that's all fine. And so it looks like that scalar multiplication here is fine too. And typically, yes, you do it as a pair. You can't usually get away with just redefining addition because addition and scalar multiplication are usually tied together. Like if I say 2 times something, that's usually the same as adding the thing twice. So they are related. You usually have to change them both. And you can kind of feel that here, right? Addition says add the two components, add x and, sorry, multiply x and a. So if I had x and x, that'd be like taking 2 x's, but what does 2 x's look like? Oh, in our new world, that would be x to the 2x squared. So these two operations do have to be tied together. So let me blow your mind some more. When is 0 not 0? When it's the 0 element in W2. What do we mean by the 0 element? It's the element that if I add it to any vector, I get the same vector back. So let's let our 0 vector be some a and b unknowns. A, b unknown yet, unknown. I'm doing that just because all the calculations that hinge on this are related to the actual vectors. So then we need AB plus XY to equal XY. But AB plus XY is equal to, by our rule, by our air quotes plus operator. What is it equal? Well, anytime I add, in quotes, 2 vectors here, I multiply the coefficients or multiply the components. So it's a times x and then b times y. Where now that we're down to the reals, this is just regular real multiplication. No. Well, then exactly 1, 1, you got it. So that this has to equal that. Well, the only way for that to work is if a is equal to 1. So a has to equal 1 and b has to equal 1. So in this space, so in W2 with this new plus and scalar multiplier operator, the 0 element is equal to the coordinates 1, 1. Boom, that's awesome. Yeah, so anyway, just to let you know that mathematicians spend a lot of time making weirder things. Again, this actually isn't that weird if you think about it. This is actually turning, instead of talking about addition, this is sort of like multiplication and power. Instead of going from plus to multiplication, so like 2 times something is the same number added a bunch of times, now we're doing multiples and exponents, which actually have the same kind of structure to them. So it's less weird than it might look, but it sure feels weird the first time you see it. So let's talk about the negative. So because we're just wrapping up on time here. What does it mean to be the negative in this context? Well, this is going to feel weird again. Let's make some new letters. Let CD equal minus XY. So remember, this is not just, actually, we don't even know this yet. This is not minus 1 times XY for now. It's just, it's a package. It's like this whole thing is just some vector. Just some vector satisfying minus XY plus the vector XY. So this whole package plus XY equals the 0 vector. Oh, but what does that actually mean for us? What we know about this is that if I take C and D and I add it to X and Y, so this is what I'm calling my negative version, my negative XY. When I add those together, if it is actually the negative, I should get the 0 vector. But wait, we just found the 0 vector was 1, 1. But we also know that CD added to, in air quotes, X and Y equals C times X and then D times Y. Again, with this being real multiplication, regular, good old real multiplication. Ugh. I'm rushing, I apologize, multiplication. And that has to then equal 1, 1. Well, that means that CX has to equal 1. And that means that I'm looking for C. I really want to know what C is. C is 1 over X. And similarly, D is 1 over Y. So for XY, and any point XY in W2, the negative version of it, what means the inverse of it, is actually equal to 1 over X and 1 over Y, which again, thinking about what we're doing here, where we're kind of multiplying instead of adding, well, instead of subtracting, we're dividing. So it kind of fits that meta thing. All right, let me pause there. I think that's where I want to stop. Yeah, that's definitely where I want to stop. So let me try to catch up on some of the comments that have been flying by. Yes, so Carter's question, does this mean that some of the previous examples that we saw would have been vector spaces if we had played around with them? Some of them, yes. Some of them, no. There's no salvaging the integers and the natural numbers. There might have been ways to salvage the X plus Y equals 1, maybe if you redefine your plus and multiplication. Yeah, if you broaden your mind there, maybe there's a way to make it work. Why would you just change the plus and times when you could just change the number set? That is an interesting point, yes. So you can do both. Generally speaking, unless you're in pure math, like we're not even talking Apple math, hard math, we're talking like the out there pure math. That's when people sort of experiment with stuff and go, what are the limits of it? Like, how far can I push this in weird ways that no one ever thought of when they were just trying to count, wheat sheaves back in the day. So it depends on what your goal is. For most engineering applications, you will never see anything besides regular scalar multiplication and addition. That's kind of the world we live in. The key thing we're going to need it for is more different sets. You're absolutely right. All right. Let's see what else we got in here. Yes, so this is Avery's question. So we'll usually be given the rules and then asked to prove. Absolutely. You will not have to invent your own plus and scalar multiplication. You will not have to invent those. We will give them to you, and then you have to assess it, whether it's a vector space or not. Okay. All right, I'm going to freeze there. I'm happy to stay around with questions. I know we're at 24 after, and it's already been a long day for you. So W3 next year is going to be something else. Absolutely. Now you can do W3 now. It's just the same thing in 3 dimensions. So we'll pause there. If people have questions they'd like to ask again, if I missed them in the chat, please just let me know. And otherwise, we will see you on Thursday afternoon. Thank you very much, and enjoy the rest of your evening.
I had a quick question.
Please go ahead.
So when we were looking at V naught, which is an element of the reals, we found that the 0 point or the 0 vector was 0, 0.
Yes.
Is that always the case with the reals, or it's just for that situation?
It's not so much the reals as it is about if we're using the plus and scalar multiplier that you're used to. Because if we're going to add these things, we're doing the normal addition, then the only way to start with one vector and get the same vector back is to add 0, 0. Notice that we were still in that same kind of space, like we're still dealing with 2D vectors with that weird space. And there, all of a sudden, the 0 element was not made up of the 0, 0 components. It had the 1, 1 component. So it's more about the operator, how you define plus and scalar multiplication.
So would it always be, like, if it's not a weird, would it always be 0, 0, or it depends on the case?
No, if you're dealing with, actually, we're going to see this next week a little bit. So you're asking a good question of how stable is this stuff? Basically, if we're dealing with the sets that we know and love, like all these guys, once we know a set's a vector space, we often then start taking little subsets of it, like V0. Hey, let's take part of R2 but keep the same plus and multiplication. In that case, yeah, the 0 is always the same 0 as it was for the original set. As if you're just kind of shrinking down, like maybe taking a plane in R3 or something like that, it'll be the same 0 operator as it was for the original thing that you kind of understand to start with.
And so when you have C infinity, would it's just when the function is on the 0 line, or is it still?
Yeah, exactly.
0?
No, so whatever your element, it has to be an element of your set. So in R3, the 0 vector would be 0, 0, 0, so 3 zeros. The C infinity function, it's the function that's always 0. Likewise for polynomials, it would be the function that's always 0. That always has to be, your 0 thing has to be one of whatever the set you're looking at is.
Okay, so like for the C infinity, it won't change depending on like if it's sine or cos. It'll just always be like when like a function equal to 0 instead of the origin.
That's correct. Yes. Yes. Because
Okay.
in that set, if I add the 0, again, assuming it's the usual plus and scalar multipliers, then yes, no matter what your function is, if you add the 0, always 0 function to it, nothing changes.
So does the same apply to the weirds? So like, is it always going to be 1, 1, or is that another case where
No.
or is that where it depends on the situation?
So once we've changed the plus and scalar multiplication, but we found that, okay, in this space, the 0 element is 1, 1. That'll be true even if we start slicing and dicing. As long as we have the same big set that we're working with and the same operators, the 0 element doesn't change. That's really the combination. As long as you have the set and the operators in your mind, then the 0 element stays the same.
Okay, because with the weirds, like to find the 0, 0, like the 0 element, like my brain kind of did it like where you did the inverse to try to solve for what it does.
That's totally fair.
Would you do that if it was a different situation, I guess?
Yes. So
will that always apply since it's since your addition is a multiplication? Will you always kind of be able to do the inverse?
Yes. So because our operator for plus was that multiplication at the end of the day, that's what led it to be. That's what let the 0 element be 0, 0 when we went through that calculations right previous page. When would that change? If we change what plus meant, then you'd have to go and redo that kind of calculation. But if we keep plus the same way and we basically keep the set basically the same thing, then all this logic is really hinging on what plus means. So this would not change if you kept the same plus meaning.
Okay, so like if for now, like if weird is still defined as the multiplication instead of an addition, like the regular addition, it would be always 1, 1.
Exactly, because this line here would stay the same no matter what we did, because this is really hinging on what does plus mean. It means multiply the components. And if I want the new answer to not be different from what I started with, I can only multiply by 1. So that's what is really this, what does plus mean, that led to that.
Okay, thank you. That helps a lot.
Okay, you're asking exactly the right question. So, all right. So Jenica had a perfect question. Why are we doing this? Why can't we just call it times and whatever? The purpose of this is to literally broaden the mind in terms of what we have this lockstep idea of what plus has to mean, but we're trying to shake that a little bit and just say, if you're willing to consider other options, plus doesn't have to mean what it's always meant for the quite frankly, the limited kinds of spaces you guys have worked in so far. Yes, it's good for 99% of most of humanity, probably a few more decimals after that, but the same rules apply to this kind of redefinition of plus and scalar multiplication. And as soon as we do that, that lets us do different things. And sometimes that's handy. Usually more for the Apple math and phys type people, but sometimes it's handy. All right. So undefined, this is redefined. Right. So that's an excellent question. I think this is from, Kyle. So there is a transition. Our plus here applies to 2 elements of the set. But then when we do that, we kind of went back to regular multiplication. That was sort of under the hood. And that's pretty typical of these cases where the first step is the crazy definition of plus and scalar multiplication. But in fact, we're actually defining it. As soon as you say x times a here, what we meant was real multiplication of 2 real numbers, because we're not in this set anymore. We're just in 2 real numbers land. And so, yeah, we get a single real number back. I know titanium, don't know radioactive. All right. Let's go. Are there ever 2 operators at a time for a vector space? Sorry, I'm not sure if Max is still here, but I'm going to answer it anyway. So only 2 operators at a time. A vector space only needs 2 operators, and we only test the 2 operators. When you get into other things called rings and fields and groups, then you have elements. It's like getting dot product and stuff like that in there too. So it can get more fun. We are not going to get more fun in this class. And yeah, so yeah, it does need to be defined in terms of the conventional operators. Pretty much, yes. That's at some point we have to go back to some ground truth about how numbers work. And so this definition here is relying on us knowing what regular real numbers multiplication means. Yeah. Okay. Let me just pause there. I think that's all. I think please do. I was going to say, go for it.
Okay. Is there any way I can watch the synchronous lectures without losing like the clicker marks? Because I really like.
Oh, there's no clicker marks. There's no marks. It's just for fun. Nope, just for fun.
All right, never mind then.
Okay. Awesome. Yeah, no problem. So yeah, just watch the recordings and you're good.
Hi.
Hi.
Could you just repeat like the original like basis reasoning for multiplying these 2 numbers together? I'm just gonna watch that.
Like when we're doing this weird plus operator, you mean?
Yes.
Right. So that comes from someone telling us that that's what they want. So here we said, all right, I'm going to look at the set. And that was the set makes sense. Go back here a second. So we're going to talk about this set upper quadrant without the axes. And then they said, all right, for the purposes of any 2 elements in that upper corner, I'm going to define what we mean by plus to mean not what you mean by plus as a default, but this operation here. So this is using our function definition of what's my function name? What does it take in? It takes in 2 elements of W2 and it spits back a new element of W2. And how does it do it? How do we define the actual transformation? You hand me an XY and an AB as 2 elements. So pick 2 random numbers. The new vector is going to be 2 real numbers as well. And we're going to compute those by XA giving the first component and YB giving the second. So it's really this line here that defines it.
Oh, okay. So like at the top where we're defining the plus, could technically we just write anything? And because that means multiplication, we can write whatever we want.
That's right. You could have said 16A and 4BY squared. Absolutely.
I mean, like in the first line, the top line, it says plus and then the colon. Could instead of plus, we write like a division sign, and then at the bottom we write the division sign as well, and it means the same thing? Is that what you mean with defining it? Or does the plus actually?
Yes. Yeah. I mean, yeah, basically, sorry, the partnership really should be this. So if we said I'm defining a vector space, it has W2 and some, let's call it division operator, or the divide operator, that's a little easier to read. 0 can divide and some dot in the box thing here. The implication is this is what you mean by addition and has to satisfy the addition rules. And this is your
Right.
scalar multiplication. Yeah. So whatever you call it, fine.
Yeah, okay. And but like not every line or like does the plus need to be redefined every time? Because here the plus is defined as the multiplication in the top line, right?
Mhm.
So every time we do this, do we need to write that or like explain what the plus represents?
It'll either be one of two things. Either we'll say plus means the usual thing. And so that's if you're in like a real numbers, function spaces, or 3, 2, 3 n-dimensional vectors, then we know what we all have a common idea of what that plus means. And we'll say that the usual addition and scalar multiplication definitions.
Okay.
As soon as we don't mean that, then we better put something precise like this, what's on the
Okay,
page
good.
here.
Yeah, that helps a lot.
Okay. Stacey's question. So plus doesn't always mean this. So this is where we often use short form. So when we say W2, especially the W2 now, this will be a, hey, this is not R2. This is not any sort of regular set. And so the implication is it's probably this weird plus. I mean, we'd tell you again if it was in the context of an assignment or a test, but by saying W2, we're kind of prompting you, hey, we've seen this W2 in class and it's that weird set and this weird plus and that weird dot. What's the question again? Sorry. So
Sorry, I
is
can
it always
explain my question if that was unclear.
Sorry, go ahead. Yeah.
Yeah, so we're saying that this weird plus means where you multiply like the first part of the vector by the first part of the other vector, and then
Right.
the second part by the second part. So is that always what the plus means? Like that weird plus is defined with these rules always, or can that change?
In this
Like, based on the
W2
question?
that we're talking about, this is what we'll mean by W2 from now on. Yes. We will
Okay.
have other occasions where we define plus in other ways,
Right.
but we'll give you a prompt that it's not W2 anymore.
Okay, got it.
So,
Thank you so
yeah.
much.
We can get other bizarre ones too. Yeah, sorry, I just saw Melanie's question there. Yeah. So the notation here is just, this goes right back to the first slide. I won't go back. I will. I have to go back to the first slide. I can't resist. All right. So let me see if I can do this. Does that work? There we go. Yeah. All right. So there we go. That's better. All right. Where's that definition? Yeah. So in some sense, if we're going to be talking about what are we asking? What's the question we're asking? Hey, is this thing a vector space or is it not a vector space? We're trying to divide things into is or is not vector spaces. Once we do that, we're like, well, what do I need to know to say is it or not? And it turns out the things that we need are a set and these two specific functions, whatever we're going to call plus and whatever we're going to call a scalar multiplier. So the notation that we developed is if you want to fully tell me what your vector space is, where did that notation go? That was in the first slides. Anyway, so if we go down this list of catalog stuff here, if you want to test whether something is a vector space or not, then we have to know what you mean by plus, you have to know what you mean by scalar multiplier, and we have to know what you mean by the set V. So we usually write it as this triple, a potential vector space, let's call it that way, because it might not be one. A potential vector space is something where you've told me what your set is, you've told me what your plus means, and you've told me what scalar multiplication is. In a lot of contexts where we mean what you usually mean, and we all agree what plus means on reals and the plane and 3D, then we don't include these unless we have to. But if there's ever any doubt, the right way to introduce a vector space is say, here's my set, here's what I mean by plus, and here's what I mean by scalar multiplication. Perfect. Thanks. The floor is open again if anyone has follow-ups to any of that.
One question is regarding to I wish to access your notes and your synchronized video.
Right.
Can I have access it?
So what we're saying is anyone who's preferring to come to a different lecture time for whatever reason, usually time zones and stuff, send us an email and we'll swap you sections. So we're only letting, it's only manageable if students are only enrolled in one section on queue. It makes life miserable if they're not. So if you want to switch sections though, just send us an email at the APSC 174 account and we'll switch you over.
Okay, cool. Thank you.
Thanks. Where's our count? All right. All righty, last call for questions. Feeling pretty good. All right, then we will see you all on Thursday. Have a good night.